Welcome to Calculus 1. In this lecture, we will be going over part 1 of the precise definition of a limit. This lecture is the culmination of all the lectures that have happened thus far. If you haven't watched any of those, I highly recommend you watch them before watching this lecture. In particular, I highly recommend watching the second lecture on the real number system before tackling the precise definition of a limit. Let's first begin by talking about if-then statements. An if-then statement looks something like this. It is read, if P, then Q. For example, this statement here is read, if x is greater than 3, then x is greater than 0. This is of course true. For example, suppose that x is equal to 5, then x is greater than 3 and x is greater than 0. Now suppose that x is equal to 2. Then x is less than 3, so x is not greater than 3, but x is still greater than 0. And finally, suppose that x is equal to negative 4. Then x is less than 3, as well as x is less than 0. In summary, if P is true, then Q is true. If P is false, then we don't know anything about Q. Q could be true, but Q could also be false. If this doesn't make sense to you, I highly recommend pausing the video and looking this over before moving forward. Before getting into the precise definition of a limit, let's recall the intuitive definition. Given f is defined on some open interval that contains c, except possibly at c itself, we write the limit of f of x as x approaches c is equal to L if we can make the values of f of x arbitrarily close to L, that is, as close to L as we like, by taking x to be sufficiently close to c, but not equal to c. So far we have been relying purely on our intuition to define the limit. However, there is still some unfinished business. We must remove the ambiguity in the intuitive definition. So here I have the intuitive definition again, but I have highlighted certain parts that are ambiguous. For example, f of x arbitrarily close to L is quite ambiguous. We don't exactly know what arbitrarily close to L means. Second, taking x to be sufficiently close to c on either side of c, but not equal to c, is also ambiguous, because we're not specifying how close to c we want x to be. Let's first tackle this part. X is sufficiently close to c, but not equal to c. What I'm about to do here should not come as a surprise, because we have covered this in a previous lecture. We can make this precise by saying 0 is less than the absolute value of x minus c is less than delta. This is because the absolute value of x minus c can be interpreted as the distance between x and c on the real number line. Further, we place the condition that 0 must be less than the absolute value of x minus c, and this means that x cannot be equal to c, or the inequality won't be true. Finally, we say that the absolute value of x minus c must be less than some number delta, where delta specifies the closeness that x and c must be on the real number line. So we can make delta as small as we like, which would specify that the distance between x minus c must be very small. Again, this should not be a surprise to you because we have discussed this already. Now let's move on to f of x is arbitrarily close to L. This can be written as the absolute value of f of x minus L is less than some number epsilon. This means that we can specify the closeness that f must be to L by making epsilon a small number. In other words, f of x is no longer arbitrarily close to L, because we have set a specific number epsilon that specifies the closeness between f of x and L on the real number line. Let's focus on the absolute value of f of x minus L is less than epsilon. More specifically, how can we visualize this on a graph? Consider the function f of x shown here, where the red dot is the limit point. Here, we have the line y is equal to L. Here, we have the line y is equal to L plus epsilon. And here, we have the line y is equal to L minus epsilon, where epsilon is the distance shown here. What we're saying when we say the absolute value of f of x minus L is less than epsilon is we're saying that f of x is somewhere in this green band, and we will call this green band the epsilon band. Now let's consider what we mean when we say x is sufficiently close to c but not equal to c. Consider the same function f of x here, where again, the red dot is the limit point. In the middle we have c, and on either side we have c minus delta and c plus delta, where delta is the distance shown here. So when we say that 0 is less than the absolute value of x minus c is less than delta, what we're really saying is that x is somewhere in the orange band here. However, note the condition that the absolute value of x minus c must be greater than 0. So in fact, x can be anywhere in the orange band except for directly in the center. Now what do we mean when we say f is defined except possibly at c? For example, in our limit definition, we say let f be defined on some open interval that contains c except possibly at c itself. For example, consider the function f of x here, where c is at the point x is equal to 1. Now consider these two bars, which defines our interval. When we say that f is defined on some open interval that contains c, what we mean is that f must be defined somewhere in between these red bars. However, f does not necessarily need to be defined at the point x is equal to c. In our example here, f is always defined on some open interval that contains c, however it's not defined at c itself. So now let's finally talk about the precise definition of a limit. The precise definition of a limit is as follows. Let c and L be in the real numbers, and f be defined on some open interval that contains c, except possibly at c itself. We say that the limit of f of x as x approaches c is equal to L when the following condition is true. For all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. NANI? Okay, now let's calm down here for a second, because this isn't as complicated as it looks. Well, I think a helpful way to go about doing this is to visualize it. So let's consider the epsilon delta band. So let's first draw the epsilon band on this graph over here, where in the middle we have y is equal to L, the top we have y is equal to L plus epsilon, and the bottom we have y is equal to L minus epsilon. Now, let's put the delta band on top of the epsilon band, so it looks something like this, where in the center we have c, on the left we have c minus delta, and on the right we have c plus delta. Now what our epsilon delta definition is saying is that if x is in the delta band, that is the orange band, then f of x must be in the epsilon band, that is the green band. So let's now observe what happens when we make the epsilon band smaller. Again, we have y is equal to L in the center, y is equal to L plus epsilon on the top, and y is equal to L minus epsilon on the bottom. Now, let's overlay this with our original delta band. We have c in the middle, c minus delta on the left, and c plus delta on the right. Now let's focus our attention over here. This f of x is in the delta band, but it's not in the epsilon band. Remember what I said before. Our epsilon delta definition says that if x is in the delta band, then f of x must be in the epsilon band. But here we have an x in the delta band, but an f of x that's not in the epsilon band. So what is going on here? Does the limit not exist? Well, let's revisit our definition of the limit. It says, for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. What this means is that we only need to find one value of delta that makes this work. In other words, we can simply make delta smaller and shrink the delta band. So let's see what this looks like graphically. Well, remember, we have our epsilon band over here, where we have y is equal to L, y is equal to L plus epsilon, and y is equal to L minus epsilon. What I'm going to do now is make the delta band smaller. So in the middle, we have C. On the left, we have C minus delta, and on the right, we have C plus delta. But note that these deltas are smaller than the deltas in the previous slide. Now, if x is in the delta band, f of x will be in the epsilon band. So let's revisit our epsilon delta definition of a limit and see if we can have a better understanding. So the important part I want to focus on is for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Let's consider the first part, which says for all epsilon greater than 0. This means that epsilon can be any positive real number you can think of. To understand the significance of this, you need to watch Lecture 2, where I talk about the real number system. But in short, the significance of this is that epsilon can be any number in the open interval 0 to infinity. The next part says there exists a delta greater than 0. This means that there must be some delta that satisfies this if-then statement. So once again, for all positive real numbers epsilon, there must be some delta such that if the distance between x and c is less than delta, then the distance between f of x and L must be less than epsilon. So let's consider what happens when we make the epsilon band extremely small. Here's the epsilon band, and here's the delta band. How small can we make the epsilon band and still find a sufficient delta band? In other words, the epsilon band is the constraint. Epsilon can be any positive real number. It is up to us to find a sufficient delta band that will make it such that if x is in the delta band, f of x will be in the epsilon band. So can we make epsilon any real positive number and still find a sufficient delta? If so, then the limit exists. If not, then the limit does not exist.